Now we look at the problems in Chapter 5. First problem is from one of the Daventer's math textbook, Arithmetica. This is a problem from page 220. Find four numbers such that when any three of them are added together, their sum is one of four given numbers. Say the given numbers are 20, 22, 24, and 27. This is a problem we can use algebra to solve. There are different ways to solve this problem. So here we're going to follow the solution of Daventer's. First, we let x be the sum of all four numbers. And now we try to describe all these four numbers in terms of x. Suppose the four numbers are a, b, c, and d. By the problem, we know when we add any three of them, we get these four numbers. So for example, if we add three of them, a, b, c, we can get 20. And we can add a, b, d, we get 22. a, c, d, we get 24, and we add b, c, d, we get 27. So these are numbers given. Because there are only four different ways of picking three numbers out of four numbers. So that's all we have. Next we're going to do is to express a, b, c, d, these four numbers in terms of x. Because we know when we add all four numbers, we should get x, because that's what we assumed. X is the sum of all four numbers. So if we add, that means we add a, b, c, d, we should get x. But we also assume that if we add three of them, a, b, c, we get 20. So clearly that means d is x minus 20. Because four of them is x, three of them is 20, that means the fourth one is x minus 20. Similarly, we can find c and b and a in terms of x by the rest of the equations. So three of them, a, b, d is 22, a, b, c, d is x. That means the missing one, c, is x minus 22. And similarly, and the missing one here is b, that's x minus 24. And the missing one, a, here is x minus 27. And next we're going to set up an equation to solve for x, because we cannot stop here because we don't know what x is, and we need to find out those numbers a, b, c, d. We add these four numbers a, b, c, d, we should get the sum of these four numbers, that is also x. The next step, how to get this equation, this is from the definition of what sum is. So we add a, that's x minus 27, and b, x minus 24, and c, x minus 22, and d, x minus 20. We add these three numbers a, b, c, d, we should get the sum, which is x. That's what we assumed. Next step is very easy. So if we had any algebra class, we should know how to solve this equation. We combine like terms on the left side. X plus x plus x plus x, we get a 4x. Minus 27, minus 24, minus 22, minus 20, we get a minus 93. And next, we're going to combine these two x terms on the left side and the right side by subtracting x from both sides. So 4x minus x, we get 3x. And the right side, x minus x is 0. And we add 93 both sides, so we get 3x equal to 93. So I skipped one step here. And the very last step, divide x. We get a divide by 3, so we get x is 31. And remember, x is only the sum of these four numbers, and we want to find these four numbers, which means a, b, c, d. And if we use this expressions here, we can find out a, b, c, d, just plug in x. So d is 31 minus 20, c is 31 minus 22, b is 31 minus 24, and a is 31 minus 27. So we get these numbers. So the answers will be 4, 7, and 9, and 11. So this example, we instead of trying to find ABCD directly, we try to find the sum first. When we get the sum, we can find the other numbers easily. So the first homework assignment, number 1 on page 231, is very similar to this. Daventer's textbook book arithmetic has 189 problems in there, and so this is one of them. And next we look at a Daventon equation. What is a Daventon equation? It looks like this example here on page 228. So this is an example of Daventon equation. If we look at it, it has two variables, x and y, and the coefficients a, b, their numbers will be given, and the right side is a constant that's also given. So the idea of solving this equation is to find one particular solution for x and y, because clearly we have two unknowns and we only have one equation. That means solutions will be not unique. So we have infinite many solutions. And first we find one particular solution for x, one particular solution for y, and then we're going to use the formula given in the textbook to find all the other solutions. In the formula, this is the formula on page 226. In the formula, x represents the unknown, so that's what we want to solve, and y is the unknown we want to solve. x0 and y0, they represent a particular solution we found. So that's what we need to find first. And b and a, they're just coefficients in front of x and y. And d means the greatest common divisor of the coefficients of x and y. T is arbitrary integer, any integer, like 0, 1, 2, 3, or -1, -2, -3. Whenever we plug in an integer, we get one solution. Because there are infinite many solutions, we have infinite solutions for x and y. So first of all, we want to find out x0 and y0. How to find them? We're going to apply Euclid's algorithm to find the greatest common divisor first. This has been explained in last week's video. So if you have trouble finding the greatest common divisor of 195 and 221, you can go over the example in the last video. So basically we divide the big number by the smaller number and keep dividing and until we reach 0, remainder 0. And the last non-zero remainder is the answer, the greatest common divisor. So first step, we apply Euclid's algorithm to find the greatest common divisor of a and b. A is the number in front of x, b is the number in front of y. So we can drop the negative sign here because the equation can also be considered as 195x minus 221. So we found the greatest common divisor, it's 195 and 13. And we also explained we can, in last week's video, we can express the greatest common divisor as a linear combination of these two numbers, original numbers, 195 and 221. This just is part of the Euclid's algorithm. We can use back substitution, keep plugging back to find these two numbers, 8 and -7. So if you don't remember, you can go over the last video from last week. Now we found out 13 is equal to 8 times 195 plus -7 times 221. If we compare this equation, this expression and the original equation, it's very close. The left side we have 195 times something, 195 times something, and we have 221 times something, and we have I guess I should put 7 times -221. That's the expression we can find from Euclid's algorithm. And instead of having 65, we have 13. So we need to get a 65 in order to get close to original equation. So we multiply 5 because 13 times 5 is 65. We get 65. That's what we want. And the right side, when we multiply 5, we try to keep original numbers 195 and negative 221. So we multiply 8 by 5, we get 40, and we multiply 7 by 5, we get 35. And if we switch the numbers to make them look like the original equation, so by the commutative property, we can switch 40 and 195. So we get 195 times 40 plus negative 221 times 35. If we look at this equation, 65 and the very right side, the 65 is the same as 65 in original equation. And the other side, 195 times something, 195 times something plus negative 221 times something plus negative 221 times something. So this expression, then we can see the red numbers 40 and 35, they fit original problem, which means 40 and 35 are one particular solution of original equation. So that's how we get x0 is 40, y0 is negative is positive 35 here. That's just from by comparing the expression we get from Euclid's algorithm and the original problem. The next step, we're going to find out all possible solutions by using the formula. So we know x0 is 40, y0 is 35. We still need well, actually we have everything. We have a, that's 195, that's the number in front of x. B is negative 221, number in front of y. D means the greatest common divisor, that's 13. And so plugging everything in there, x0 40 plus b negative 221 divided by d, which is 13, times t equals 40 minus 7, negative 17. Simplify, negative 221 divided by 13. So that's x. So x is 40 minus 17t, and y is y0, which is 35 here, and minus a over d. A is 195 over d, that's 13 times t. So we get y equals 35 minus 15t. And the t here is any integer. So if we, for example, if t is 0, we can get 14 minus 17, that's 23, and for x, and I'm sorry, if t is equal to 0, we get x equals 40 and y equals 35. If we plug in, they must be a pair of solution, and that's what we get. Actually, original one particular solution. If t is 1, we get 40 minus 17, that's 23, and 35 minus 15, that's 20. So also 23 and 20 should be another pair of solutions. So if we keep plugging numbers for t, 0, 1, 2, 3, 4, and so on, and negative 1, negative 2, negative 3, negative 4, and so on, we can get infinite many solutions. So that's how we solve the Fenton equation. Found one particular solution first by using Euclid's algorithm, and then plug into the formula. And the formula, we skipped the proof of the formula, so these can be verified by plugging into original equation, ax plus by equals c, and we can verify they are both solutions. So the homework assignments 14a is on page 231 is similar to this.